There is a relationship between the number of moles of gas in a sample and the volume that that gas occupies. It was noticed that when gases react at the same temperature and pressure, that their combining volumes were always in simple whole number ratios. For example, if we look at the reaction between hydrogen gas and chlorine gas to produce hydrogen chloride gas, what we can say is that every 1 volume of hydrogen gas will react with 1 volume of chlorine gas, and it will always produce 2 volumes of hydrogen chloride gas. This is based upon the coefficients from the balanced equation. The volumes could be measured in units of milliliters or liters, really any unit that we use to measure volume. Avogadro's principle says that for gases that are at the exact same temperature and pressure, equal volumes of gases will contain an equal number of moles or molecules of that gas. So the volume of a gas is directly proportional to the number of moles. This means that in reactions of gases, their volumes and their number of moles must be the same. When we look at the coefficients of a balanced reaction, and that reaction is involving gases, the ratio will tell us not only the mole ratios, but also the volume ratios that those gases will react in. So our ratios for our hydrogen chloride formation is 1 to 1 to 2. Those coefficients also tell us the volume ratio, so 1 liter to 1 liter to 2 liters. We can use this in order to solve stoichiometry problems where reactions are involving all gases. Methane burns according to the following equation. The combustion of 4.50 liters of methane consumes how many liters of oxygen if both volumes are measured at 25 degrees Celsius and 740 torr? We don't actually have to use the temperature and the pressure in this problem, but it's important that we're working at a constant temperature and pressure if we're going to talk about what the volumes of the gases are. We would start with our 4.5 liters of methane, and we can quickly work to figure out how much oxygen is required to react with the methane by using Avogadro's principle. The coefficients of our balanced equation, 1 to 2, tell us the volume ratios that will react. If we start with 4.5 liters of CH4, we know that 1 liter of methane needs to react with 2 liters of oxygen. Those coefficients don't just tell us mole ratios, but in a gas they also tell us the volume ratios. Our liters of methane would cancel, and we'd be left with liters of oxygen. This works because everything in our equation is a gas, and the two things that we're moving between, the methane and the oxygen, are both gases at the same temperature and pressure. So we can apply Avogadro's principle as a shortcut. So 4.5 times 2, we'd end up with 9 liters of oxygen gas that would be required to react with exactly our 4.5 liters of methane gas. How many milliliters of oxygen measured at 20 degrees Celsius and 755 torr are needed to react with 180 milliliters of nitrogen monoxide measured at the same temperature and pressure? In this example, we're starting with 180 milliliters of our nitrogen monoxide gas. We can work to figure out our unknown amount of oxygen gas, our volume of oxygen gas, by using Avogadro's principle. We're at the same temperature and pressure, so we can use our coefficients out in front. 2 volumes of nitrogen monoxide gas will react with 1 volume of oxygen gas. So starting with our 180 milliliters of nitrogen monoxide, we can say that 2 milliliters of nitrogen monoxide will react with 1 milliliter of oxygen. Our milliliters of nitrogen monoxide will cancel on the numerator and the denominator, and we'll end up needing 90 milliliters of oxygen for this reaction. Avogadro's principle implies that the volume occupied by 1 mole of any gas, which is known as its molar volume, must be identical for all gases under the same conditions of pressure and temperature. Molar volume has the abbreviation of V sub m. Molar volume can be measured at a set of conditions known as standard temperature and pressure, STP for short. The standard temperature is 0 degrees Celsius or 273 Kelvin, and the standard pressure is 1 atmosphere of pressure. At conditions of standard temperature and pressure, 1 mole of any gas will occupy the exact same volume. So our molar volume at STP is 22.4 liters. So that's going to be 22.4 liters of hydrogen if we're at standard temperature and pressure and we have 1 mole of it, 22.4 liters of helium if we're at STP and we have 1 mole of it. It doesn't matter what the identity of the gas is. If we're at standard temperature and pressure, the volume that 1 mole of gas occupies will always be the same. Let's look at 3 different gases as examples. If we have 1 mole of helium in a balloon, that would be 4 grams of helium. And if we're at conditions of STP, 273 Kelvin and 1 atmosphere pressure, then our balloon would occupy 22.4 liters. If we have 1 mole of oxygen in our balloon, that would be 32 grams of oxygen, since oxygen is a diatomic molecule. And at conditions of standard temperature and pressure, that balloon would also occupy 22.4 liters. If we have 1 mole of nitrogen, which is another diatomic gas, that would be 28 grams of nitrogen. And if we are at conditions of STP, that balloon would be 22.4 liters. At our molar volume at standard temperature and pressure is always going to be right around that 22.4 liter mark. We can use the molar volume of a gas at standard temperature and pressure in order to convert between moles and volume. So notice that we can write that as a conversion factor, 1 mole of gas to every 22.4 liters, or we can flip our fraction around and say 22.4 liters for every 1 mole of gas, as long as we are at standard temperature and pressure. So looking at the picture on the left here, that allows us to interconvert between volume and number of moles. That's our molar volume. We can convert between moles and particle units by using Avogadro's number, N sub A. And we can convert between moles and mass by using our molar mass for our given compound. How many liters of hydrogen gas measured at standard temperature and pressure are needed to combine with exactly 1.5 liters of nitrogen, also measured at standard temperature and pressure, to form ammonia? So first let's write our chemical equation. We have hydrogen gas reacting with nitrogen gas to form ammonia, which is also a gas. We're going to have to balance our equation. 3 moles of hydrogen will react with 1 mole of nitrogen to form 2 moles of ammonia. We can solve this problem 2 ways. The first way is we can use the molar volume at standard temperature and pressure. The molar volume, we said, was 1 mole of a gas takes up 22.4 liters of space. Since we're at standard temperature and pressure, we can use this relationship. Starting with our 1.5 liters of nitrogen, we could convert our volume into moles. Since we're at standard temperature and pressure, the volume of nitrogen will be 22.4 liters per mole of nitrogen. This will get us into moles. Now that we're in units of moles, we could go from nitrogen over to hydrogen by using our balanced chemical equation. 1 mole of nitrogen reacts with 3 moles of hydrogen. And we're trying to determine the number of liters, the volume. So since we're at standard temperature and pressure, we can say that 1 mole of hydrogen gas will occupy 22.4 liters of space. That'll be its volume. Notice that our liters of nitrogen will cancel, our moles of nitrogen will cancel, our moles of hydrogen will cancel, and we'll be left in liters. When we solve it this way, essentially our molar volume is canceling itself out. We end up getting 4.5 liters of hydrogen gas that will be required for the reaction. Since we're at standard temperature and pressure for our reactants and our products, we haven't changed our conditions. We could also use our shortcut method of using the coefficients as volume ratios, and we'd end up with the same answer. So starting with 1.5 liters of nitrogen, and then looking directly at the balanced chemical equation, we know that 1 liter of nitrogen will react with 3 liters of hydrogen. So 1 liter of N2 reacts with 3 liters of H2. This is more of a direct method. Our volume of nitrogen cancels and we're left with our volume of hydrogen. So we'll have 1.5 times 3 or 4.5 liters of hydrogen. So there's two ways that you could go about approaching this problem. The only time we use that molar volume of 1 mole being 22.4 liters is when we're at standard temperature and pressure. But since both of our reactants were gases, we could use our shortcut of the coefficients also being volume ratios. The ideal gas law is an equation that tells us how the 4 important variables for a gas, pressure, volume, number of moles, and temperature, are related. If we know 3 of these values, we could calculate the 4th one. The ideal gas law is written as PV equals nRT. P is the pressure in units of atmospheres. V is the volume in units of liters. N is the number of moles in units of moles. Temperature is in units of Kelvin. And R is known as the universal gas law constant. It has a value of 0.0821. Its units are important because it determines the units that everything else must be. Liters times atmospheres over moles times Kelvin. An ideal gas is a perfect hypothetical gas that would obey all the gas laws exactly over all temperatures and pressures. The following assumptions are behind the scenes for any ideal gas. The space that the particles of the gas occupy themselves are so small that we consider them negligible. And the gas particles essentially have no intermolecular forces between them, so they're not attracted to each other, nor are they repelled by each other or the walls of the container that they're within. Let's practice using the ideal gas law. If a 53.4 milliliter light bulb is filled with argon at a temperature of 21 degrees Celsius and a pressure of 2.28 torr, how many grams of argon are in the light bulb? Our ideal gas law is PV equals nRT. And if we're going to determine the number of grams of argon, the only thing in the ideal gas law that is related to grams would be the number of moles. So we're going to want to rearrange and solve for N. N will be equal to pressure times volume divided by R times T. So we're going to have to get our hands on everything else in order to figure out the number of moles. Our volume is given to us directly, 53.4 milliliters. But remember, we have to be in a certain units for everything because of our gas law constant. So we're going to have to convert our volume to liters. That'll be 0.0534 liters. Our temperature is 21 degrees Celsius. And we're going to have to add 273 in order to convert to Kelvin. That'll be 294 Kelvin. Our pressure is 2.28 torr, and we have to be in units of atmospheres. So our link between torr and atmospheres is that 760 torr is equal to 1 atm. Our units of torr will cancel, and our atmospheres should be 3.03 times 10 to the negative third atm. And R is 0.0821 liters times atmospheres divided by moles times Kelvin. Now we're ready to plug everything into our ideal gas law. N will be equal to our pressure times our volume, so 3.03 times 10 to the minus third atmospheres times 0.0534 liters divided by R, 0.0821 liters times atmospheres over moles times Kelvin times our temperature, which is 294 Kelvin. Before we do any calculations, make sure that our units cancel and we're left with the correct units. Our atmospheres will cancel, our liters will cancel, Kelvin will cancel, and in the denominator we're left with 1 over moles, which is really just moles. So N, we should get 6.64 times 10 to the negative 6th moles, and this is of the gas argon. We were asked to figure out the number of grams, so we can look at the periodic table to determine what the molar mass of argon is. 1 mole of argon is equal to about 40 grams. So our moles will cancel. When we multiply, we'll end up with about 2.7 times 10 to the negative 4th grams of argon. Let's try another example. What volume in liters does 0.136 grams of oxygen occupy at 20 degrees Celsius and 748 torr? So starting with our ideal gas law, PV equals nRT. This time we want to rearrange and solve for the volume. So our volume will be equal to nRT divided by P. Making sure that we have the correct units for everything. Our temperature is 20 degrees Celsius, and we need to add 273 to convert to Kelvin. So that's going to be 293 Kelvin. Our pressure is 748 torr, and we're going to have to divide by 760 torr because that's our conversion between torr and atmospheres. So our units of torr will cancel. Our atmospheres will be 0.984. N is our number of moles, but we were given grams, so we're going to have to calculate moles. We have 0.136 grams of O2. And when we convert between grams and moles, remember that oxygen is diatomic. So 1 mole of oxygen is not going to be 16 grams, but it's going to be 32 grams. Our grams of oxygen will cancel, and our moles will be 4.25 times 10 to the negative 3rd. Now we have everything we need in order to solve for our volume. Our volume will be equal to N, which is our moles, 4.25 times 10 to the negative 3rd moles, times R, which is 0.0821 liters times atmospheres over moles times Kelvin, times our temperature, 293 Kelvin, divided by our pressure, which was 0.984 atmospheres. Checking to make sure that all of our units cancel. Moles cancels, atmospheres cancels, Kelvin cancels, and we're left with, in the numerator, liters, which is what we want our volume to be in. So our volume in liters should come out to be 0.104 liters. We can use the ideal gas law in order to calculate the molar mass of a gas. Molar mass is defined as the grams per mole. So let's call that the mass over the number of moles. We'll use the little symbol m to represent mass. And that mass can be in grams. Moles we talked about in our ideal gas law, and the symbol we used for moles is lowercase n. So starting with PV equals nRT, we can rearrange the ideal gas law and solve for the number of moles. N will be equal to the pressure times the volume divided by R times T. Imagine plugging that in to the denominator of our molar mass equation. We would end up having lowercase m for the mass over the number of moles, which is PV over RT. And to simplify this fraction, we can think about writing it as m over 1 times RT over P times V. So therefore, the molar mass will be equal to the mass times the gas law constant times the temperature divided by the pressure times the volume. You could calculate the number of moles separately if you wanted to, and then divide those number of moles by the grams, but this is just a simplified equation that combines the two concepts, the ideal gas law with molar mass. A gas was isolated in a bulb with a volume of 255 milliliters at 25 degrees Celsius and a pressure of 10 torr. The gas weighed 12.1 milligrams. What is the molar mass of this gas? We just derived the equation that the molar mass of a gas can be calculated by taking the mass in grams times R times T divided by the pressure times the volume. Our volume is equal to 255 milliliters, which equals 0.255 liters. Our temperature is 25 degrees Celsius, which equals 298 Kelvin. Our pressure is 10 torr, converting to units of atmospheres. So we're going to divide by 760 torr. We're going to end up with 1.3 times 10 to the negative 2 atmospheres. And our mass was given to us in units of milligrams, and molar mass is defined as grams per mole. So converting our milligrams into grams, 12.1 mgs will equal 0.0121 grams. Now we have everything we need in order to solve for the molar mass of the gas. Molar mass will equal 0.0121 grams times 0.0821 liter atmospheres over moles times Kelvin times our temperature, which is 298 Kelvin, divided by our pressure, 1.3 times 10 to the negative 2 atmospheres, times our volume in liters, 0.255 liters. Checking to make sure everything is in the correct spot. Our atmospheres cancel, our Kelvin cancels, liters cancel, and notice in the numerator we have grams over moles that we're left with. So we are calculating a molar mass, and we do have the correct units. Our molar mass for this gas comes out to being around 89.3 grams per mole. We can also use the ideal gas law to calculate gas densities. Density is defined as mass per unit volume. Gases are very light, and so their densities are measured in grams per liter, rather than in the familiar grams per milliliter or grams per centimeter cubed. Gases become less dense as the temperature increases, and gases will become more dense as their pressure increases. So let's use the ideal gas law in order to solve for an equation where we can calculate the density. Density is mass per volume. So mass we defined as lowercase m, and that is in units of grams. PV equals nRT is our ideal gas law. If we rearrange and we solve for the volume will be equal to nRT divided by the pressure. Density will equal mass over volume, so mass over nRT divided by P. And we can simplify this fraction by saying m over 1 times the pressure over nRT. So this would be mass times pressure over nRT. And here we have m over n. So grams per mole. M over n is simply our molar mass of our gas. So we can simplify this even more. Our density will be equal to the molar mass of our gas times the pressure divided by R times T. And because molar mass is in the numerator, that means that the density of a gas is directly proportional to the gas's molar mass. If a gas is lighter and has a lower molar mass, it'll be less dense. If it's a heavier gas and has a higher molar mass, it'll be greater density. We'll come back to the concept of density and effusion and diffusion of gases at the end of the chapter. For now, we're going to look at some practice problems where we use the formula we just derived. What is the density of sulfur dioxide gas at -5 degrees Celsius and a pressure of 96.5 kilopascals? The formula we just derived is that the density can be calculated by taking the molar mass of a gas times the pressure divided by R times T. Our temperature is given to us in the problem, -5 degrees Celsius plus 273 in order to convert to Kelvin. That'll give us 268 Kelvin. Our pressure is equal to 96.5 kilopascals. The pascal is the SI unit for pressure. 1 kilopascal will equal 1,000 pascals. And then we want to convert to atmospheres in order to have our units of pressure cancel with our gas law constant. And so 1 atm equals 101,325 pascals. So that's going to go in the denominator, so they cancel. And 1 atmosphere in the numerator. Kilopascals cancel, pascals cancel, and our pressure in atmospheres should be 0.952 atm. The last thing we need is the molar mass of our gas. The identity of our gas is SO2, and so we can calculate that molar mass. Molar mass will be equal to the mass of sulfur, which is about 32.1 grams per mole, plus 2 times the mass for oxygen. Each oxygen will be about 16 grams per mole. So for sulfur dioxide, our molar mass is about 64.1 grams per mole. Now we have everything we need. Our density can be calculated by taking our molar mass, 64.1 grams per mole, times our pressure, which was 0.952 atmospheres, divided by our gas law constant, 0.0821 liter atmospheres over mole Kelvin, times our temperature, 268 Kelvin. Our atmospheres will cancel, our Kelvin will cancel, our moles will cancel, and what we're left with is grams over liters, which is the typical units for the density of a gas. And so our density for this gas should come out to about 2.77 grams per liter. A liquid sold under the trade name PerClean is used as a dry cleaning solvent. It has an empirical formula of CCl2. When vaporized, the gaseous compound has a density of 4.93 grams per liter at 785 torr and 155 degrees Celsius. What is the molecular mass of the compound, and what is its molecular formula? So we know the density of our compound this time, and if we're going to figure out the molecular mass and our true molecular formula, we're going to have to take our formula for density, which is density equals molar mass times pressure divided by R times T, and we can rearrange it in order to find our molar mass. The molar mass will be equal to the density times R times temperature divided by the pressure. So first we have to find the molar mass of our compound. Then when we find the molar mass, we can come back to the empirical formula that we were given and use that in order to figure out what our true molecular formula is. So plugging into our rearranged formula, let's find our molar mass first. Our density is 4.93 grams per liter times R, 0.0821 liter atmospheres over mole times Kelvin. Our temperature is 155 degrees Celsius, which if we convert that to Kelvin will be 428 Kelvin, divided by our pressure. Our pressure is 785 torr, and we have to divide that by 760 torr to convert to atmospheres. Checking our units, Kelvin cancels, torrs cancel, atmospheres cancel, liters cancel. We're left with grams over moles, which is what we wanted for our molar mass. So our molar mass of this gas comes out to 167.7 grams per mole. So the molar mass is that of our true formula, not our empirical formula. And if you recall, we can calculate a certain number of empirical formula units. That's how many empirical formula units are contained within the true molecular formula. We do this by taking the molar mass and dividing by the empirical formula mass, which we can calculate the empirical formula mass because we were given the empirical formula in the problem. The molar mass we just got, 167.7 grams per mole, and our empirical formula mass will be that of CCl2. So if we calculate that, carbon is 12, chlorine is 35.5, and there's two of them, so it's going to be 2 times 35.5. So that should come out to approximately 83 grams per mole. And when we divide our empirical formula mass by our molar mass, we should expect a whole number, or pretty close to a whole number if you have to round. In this case, we get 2. That tells us there's 2 empirical formula units contained within the true molecular formula. So starting with our empirical formula, CCl2, we now take 2 and we multiply it through to everything within the empirical formula. So our true molecular formula for this compound should be C2Cl4. Calculating the density of a gas that is at standard temperature and pressure is very straightforward. We know that 1 mole of gas at standard temperature and pressure will always occupy 22.4 liters. And density is mass per unit volume, but at STP, we can calculate it by taking the molar mass divided by the molar volume. So for example, if we have 1 mole of oxygen gas, oxygen's molar mass is 32 grams per mole. What we have to do is take the molar mass and divide by the molar volume, which would be 22.4 liters, and that'll give us our density of O2, 1.43 grams per liter. Compare that density to carbon dioxide. The molar mass of carbon dioxide is 44 grams per mole. So to calculate the density, we take the molar mass, 44, and we divide by the molar volume, 22.4 liters. That gives us a density of 1.96 grams per liter for CO2. So we can see that the only thing that impacts the density is the identity of the gas. Oxygen is lighter, it has a lower molar mass, and therefore its density is less, only 1.43. Carbon dioxide is heavier, it has a greater molar mass, and therefore the density is higher, 1.96 grams per liter. This is a shortcut that can be used if we are at conditions of standard temperature and pressure. We can also combine the concepts of stoichiometry with the ideal gas law. Suppose a 1.25 gram sample of calcium carbonate is decomposed by heating. How many milliliters of carbon dioxide gas will be evolved if the volume will be measured at 745 torr and 25 degrees Celsius? So in this example, we're starting with a reactant that is not a gas. Calcium carbonate is a solid, and we're trying to figure out how much of our gas, carbon dioxide in this case, can be produced from decomposing that 1.25 grams. If we use our balanced chemical equation, we can figure out the number of moles of carbon dioxide that is produced. If we can figure out the number of moles, we can then come back to using our ideal gas law after in order to determine the unknown volume, which is what we were asked for. So starting with our 1.25 grams of calcium carbonate, we can convert our grams of calcium carbonate into moles of calcium carbonate. We need to calculate the molar mass. 1 mole of CaCO3 is 100.1 grams. Then looking at our balanced chemical equation, when 1 mole of calcium carbonate reacts, 1 mole of carbon dioxide gas is produced. So 1 mole of CaCO3 in the denominator to every 1 mole of carbon dioxide in the numerator. Our grams of calcium carbonate will cancel, our moles of calcium carbonate will cancel, and we'll be able to calculate the moles of CO2. 1.25 times 10 to the negative 2 moles of carbon dioxide gas are produced. Rearranging our ideal gas law, the volume will equal N times R times T divided by the pressure. We just used stoichiometry to figure out the number of moles, or N. So N is 1.25 times 10 to the negative 2 moles. R is 0.0821 liter atmospheres over mole times Kelvin. Our temperature was 25 degrees Celsius, which is 298 Kelvin, divided by our pressure, which is 745 torr, divided by 760 torr per 1 atmosphere. If you would like to calculate your pressure separately first, you can do that as well. Our moles will cancel, Kelvin will cancel, torrs and atmospheres will cancel, and all we're left with is units of liters. And our final answer here should be 0.312 liters. And because the question asked for the volume of gas in milliliters, that would equal 312 milliliters of carbon dioxide gas that can be produced. What volume of hydrogen at 27 degrees Celsius and 723 torr may be prepared by the reaction of 8.88 grams of gallium with an excess of hydrochloric acid? So once again, we're starting with something that is not a gas, so we can't use our volume shortcut. We have gallium, which is a solid, and we're trying to figure out how much hydrogen gas can be produced, the volume of hydrogen gas. So the first step will be to use stoichiometry in order to determine the number of moles of hydrogen that can be made. We have 8.88 grams of gallium, and we have to convert to moles in order to use our balanced equation. 1 mole of gallium from the periodic table is 69.72 grams. Looking at our balanced equation, 2 moles of gallium will react to produce 3 moles of hydrogen gas. So 2 moles of gallium will go in the denominator. 3 moles of hydrogen will go in the numerator. Our grams of gallium will cancel. Our moles of gallium will cancel. And our number of moles of hydrogen that will be produced will be 0.191 moles of H2. Taking our ideal gas law, PV equals nRT, and rearranging for the volume, volume will equal nRT divided by the pressure. We will just have to make sure to convert everything to the correct units. N is our number of moles that we just calculated, 0.191 moles of hydrogen gas, times R, 0.0821, times our temperature. We had 27 degrees Celsius, which if we add 273, that'll be 300 Kelvin, divided by our pressure of our gas, 273 torr, divided by 760 torr, converting to units of atmospheres. Our moles cancel, Kelvin cancels, torr cancels, atmospheres cancel, and we have liters for our volume. And we should come out to about 4.94 liters of our hydrogen gas that's produced. This flowchart serves as a good reminder for all of the different types of conversions we've seen throughout the semester. Starting with when we were using balanced chemical equations. If we had moles of a reactant A and we needed to get to moles of product B, we could look at the balanced chemical equation to move from moles of one thing to moles of another thing. If we knew the molarity, which was moles per liter, we could convert our moles into volume. If we know the Avogadro's number, which is 6.02 times 10 to the 23rd things per mole, N sub A, we can convert to particle units. Those particle units could be atoms, molecules, ions, photons. Using the ideal gas law, which is one of our new formulas, we can take our moles and figure out either the missing pressure, volume, or temperature of a substance. We could take our number of moles and calculate the volume easily if we're at standard temperature and pressure by using our relationship 1 mole of a gas is equal to 22.4 liters. That's another way to get at the volume at STP. And starting with our moles, we can calculate the molar mass. Molar mass is grams per mole in order to convert to grams of our substance. So we can figure out a lot of different things just by using some of these simple conversion factors and formulas that we've learned throughout the semester.